Okay, thank you very much for the invitation to speak and invitation to this program. I've prepared a rather haphazard collection of slides, and we can almost go through them in a random order. And I'll probably will move back and forth a lot because I've noticed that this seminar is very informal, right? So I expect many questions if any of the concepts are unfamiliar, and we can even stop. We can stop anywhere, so it really doesn't matter very much. The rate of progress, and I'll also use the word now and then if necessary. So what I'll do is still at the beginning start out. So in case the rest of the talk is boring, I'm going to start out with something at least mildly entertaining, hopefully with a historical preliminary remark on mathematics and physics rather. And so this is a comment about this famous theorem of Archimedes. Most of you know this. This is this comparison of the volume, also the surface area, actually, between the sphere and the cylinder. Right? And its legend says that Archimedes regarded this as his greatest discovery. That if you put a sphere into a cylinder like that, the volumes are related by the exact ratio, 3/2. Of course, we all know this, but it is kind of miraculous, right? That this kind of very strange shapes can have a simple ratio of volumes between them. And the legend says, I was in the midst of telling you the legend, that this Archimedes regarded this as his greatest achievement, figuring out this ratio, right? And our formula for the volume of the sphere, for example, can be easily deduced from this. So if you look at this document called the Archimedes palimpsest, for those of you with some historical interest, I do urge you to take a look. He had his first proof was what he called the mechanical method of proof. Right? He imagined setting some enlarged version of the cylinder and the sphere in some manner that balances on a lever. And he found out that if you essentially died, of course, the diagram doesn't quite convey this, but if you place the sphere and the cylinder at appropriate places with the ratio 2 to 3 on a lever, they exactly balance. That was the original proof that he gave. But this mechanical method of proof was only discovered in the late 19th century. That's why this Archimedes palimpsest was quite an important discovery. The people found this old document, so one of the multiple copies of papers of Archimedes behind some religious text, and then it took a long time for it to be deciphered. There's a book called the Archimedes, maybe it's just called the Archimedes palimpsest, I forgot, by Ruvinets and somebody else. And they give you the whole story about how this document was discovered, then it disappeared, and it rediscovered. And it's only very recently, about 15 years ago, that they started putting it together and studying it carefully. Anyways, so this is the proof that Archimedes originally gave using the method of balancing the objects on a lever. So here's a funny comment in Plutarch's passages on Archimedes, right, in his famous book, Parallel Lives. Here's what he writes. Archimedes possessed so high a spirit, so profound a soul, and such treasures of scientific knowledge that though these inventions had now obtained him the renown of more than human sagacity, he would not deign to leave behind him any commentary or writing on such subjects, but repudiating as sordid and ignoble the whole trade of engineering and every sort of art that lends itself to mere use and profit, he placed his whole affection and ambition in those purer speculations where there can be no reference to the vulgar needs of life, etc. So this is quite a remarkable passage, because sometimes mathematicians are fond of quoting this. It's trying to say, well, Archimedes was well known for all these inventions and his law of buoyancy and so forth, but all he really cared about was pure ideas and geometry, right? That's what Plutarch is arguing here. And this is a load of nonsense. There's no evidence whatsoever for this in Archimedes' own writings. Right? So this I checked. I've read a substantial portion of them myself, but I also checked with the leading experts on Archimedes. There's nothing in whatever survives of whatever version of Archimedes' writings that suggests this. Right? But it's an interesting question. Why was Plutarch writing something like this? So Plutarch, of course, was living a citizen of the Roman Empire, a rather important local functionary in the Roman Empire. But this was around the time where the idea of Greek cultural heritage was probably becoming formulated. And he regarded himself as a Greek and was doing a lot of things to propagandize this idea of a Greek civilization that was as good as the Roman one or something of that sort, right? And a lot of these political motivations appear in many places in this book. Curiously, until very recently, people didn't question too strongly anyways passages like this. So this is Archimedes' own writing in a letter to Eratosthenes. And well, we can read a little bit. I thought fit to write out for you and explain in detail in the same book the peculiarity of a certain method by which it will be possible for you to get a start to enable you to investigate some of the problems in mathematics by means of mechanics. Right? And of course, he's describing how this mechanical thought is very important for his mathematics. Right? So this, besides the fact that his papers indicate nothing of the sort that Plutarch claims, this is a direct contradiction to some extent to what he's trying to, what Plutarch is trying to argue. So of course, mathematicians like me are still inspired by the mechanical method, although mechanical means something much more sophisticated these days, right? And if you look, this is just a side comment, not at all a scholarly comment, whatever. But if you look at what the method that he used here, nowadays it would also be regarded as a rigorous proof once you have a theory of integrals. It's a completely rigorous proof, as long as you write some of its arguments as integrals. However, in those days, they didn't have integration, and somehow this idea of adding infinitely many quantities was, of course, subject to a lot of agonizing, right? And to some extent, how to add infinities is still a difference between mathematicians and physicists when it comes to quantum field theory, right? That is, physicists regard it as completely settled, but mathematicians do not, right? And that's kind of, these kind of issues are very, very old in the parallel between mathematics, physics, and also the inspiration that physics gives to mathematics. Okay, so that was just for fun, and now let's go on to the slightly more serious subject, the arithmetic topological quantum field theory. So what is this about? So I hardly need to say this for this audience, but I'll just remind you from a very formal perspective what topological quantum field theory does. So it's supposed to be like this. If you have a topological quantum field theory of dimension d, then to a closed D manifold, it's supposed to associate a number, and to close a D minus 1 manifold, a vector space, and so on. And in general, to a closed D minus K manifold, it should associate a K minus 1 category with a whole bunch of structure. So this is the idea of a fully extended quantum field theory. In particular, to a point, it associates a D minus 1 category, right? So that's the idea of a topological quantum field theory. And then if you have, say, some manifold with boundary, whatever the dimension is, it associates to that manifold, the bulk manifold, an object inside whatever category is associated to the boundary manifold. So this is the basic formal picture of topological quantum field theory as mathematicians understand it, right? So by the way, for this categorical numbering to be consistent, it's useful to regard a vector space as a 0 category and a number as a -1 category. That's rather common among certain practitioners. So because of this way of sort of formally looking at the situation, mathematicians are able to regard topological quantum field theory as just kind of an extension of algebraic topology, right? It's a functor of some sort, like homology or homotopy and things like that. So this machinery that just lays out the formal property is very convenient so that we don't have to understand path integrals and things like that, right? So in other words, from this point of view, the quantum field theory is just kind of a sophisticated function of manifolds. You know? It's sophisticated in various ways, in the way, for example, its target is various higher categories, right? But also there are morphisms between the manifolds that are reflected in this function. You know? So that's a kind of snapshot, formal view of topological quantum field theory. So what do I mean by arithmetic topological quantum field theory? Right? And sometimes this topological is in a parenthesis, as in my title, and sometimes not. I won't distinguish too carefully between the two. What I mean is you do this. So you take these objects that we study in arithmetic geometry, yeah, and plug it into the argument of a quantum field theory, right, and try to get objects similar to what you get in usual topological quantum field theory. Yeah. And in the examples that we've constructed so far, these arithmetic topological quantum field theories can be regarded as extensions, really, of the usual ones, right? So there's really kind of an extension of domain, allowing us to plug in arithmetic schemes than just manifolds. So, for example, I guess my old paper on the subject, which I like to think sort of got this point of view started, was called arithmetic Chern-Simons theory, because it seems to really extend. Although many people have pointed out I should have called it arithmetic Dicroft-Witten theory, which is correct. Sure. Sure. Okay, so I'll get to that. So I'll first give you some examples, and then we can spend as much time as you want on that question, right? So in a sense, I put the main ideas into the first few slides so that we can spend as much time as desired on the background. Okay? Yeah. Thank you very much for that question, because that's what I'm prepared for. So these are geometric spaces of the sort that you study at the intersection of number theory and algebraic geometry. See the idea, and I'll say more about it very soon. So here are some examples anyways. So before we go to a slightly more careful discussion, of course I can't go into a whole full-blown the foundations of arithmetic geometry, but here are some examples. So if you look at the integers, you can look at its spectrum. There's a scheme called its cat spectrum, and that's an example of an arithmetic scheme. And in fact, it turns out to have a topological dimension 3. And you can also take an algebraic number field, like when you join the square root of 2 to the rational numbers, or square root of -1. So that's an example. These are all examples of algebraic number field. The formal definition is the algebraic number field is a field that's a finite dimensional vector space over Q. So it has a great finiteness, right, beyond the basic field Q. So given an algebraic number field, inside there's a ring called the ring of algebraic integers, right? So in other words, if f is like q to the n, this ring of integer is something like z to the n, but with a nice multiplication. And you can take its spectrum. You can also take an algebraic curve over a finite field, something defined by, say, a two-variable equation over a finite field. These are all examples of arithmetic schemes of dimension 3. So I'll get to that as well. Yeah, thank you. Yeah, thank you. So I'm throwing the words here, and as I said, we can spend whatever time we want on explaining. Over here? Oh, that's the curve. Oh, sorry about that. I should have said a curve x over a finite field fq. Sorry. Yeah, thank you. That's just my notation. X will occur often in many different guises throughout this talk. Any other questions for now? Then the answer to many of the questions is the answer will come soon. Okay, so anyways, these are some arithmetic schemes of dimension 3. Here are some arithmetic schemes of dimension 2. Some of them will be vaguely familiar, others of them might be a bit strange. So for example, there are these fields called the p-adding numbers that you get by, you may know that you can start with the rational numbers and you can complete it at a different absolute value from the usual one. Right? You know that you can construct the real numbers as a completion of the rational numbers by taking Cauchy sequences with respect to the usual absolute value. Now, for each prime p, there's a different absolute value, and you can complete with respect to that. And you get the p-adding numbers. So in number theory, this is very important for all kinds of reasons. It's a very strange object from a purely topological viewpoint. The p-adding numbers have the topology of an infinite union of contour sets. Right. But there are other ways in which it has a certain uniform structure that make it similar to the reals. So you can take its spectrum, and similarly, completions of algebraic numbers with a spectrum of that, or power series over a finite field. Or a curve now not over a finite field, but over an algebraic closure of a finite field. These are all examples of arithmetic schemes of dimension 2. And as I said, we'll discuss the spectrum very soon. Now, there's another example here, which maybe I'll skip for now. It requires some preparation to explain. Roughly speaking, that's right. That's a very good comment. That's right. So the larger dimension is, the more complicated the structure is. And in the spirit of your question right now, I'll tell you right now, here's a scheme of dimension 1, spectrum of a finite field itself. So a finite field, in some sense, among the number systems that the number theorist works with, is the simplest one. Right? There's not much mystery over a finite field, and its spectrum has dimension 1. So if you're interested in solving equations and things like that, it's very easy over a finite field, right? And many things are simple over a finite field, and it is reflected in the dimension, as you point out. Right. And so there are also, so this is also, maybe it's good to return to later. These are some arithmetic 3 manifolds with boundary. So these, maybe I will explain the notation a little bit. This Z1 over P, this means rational numbers that only have powers of P in the denominator. So it's a somewhat bigger than the integers, but it's not all rational numbers. You're only allowing powers of P. You can see that forms a ring. You can add and multiply such things, and it's closed under those operations. So and you can take its spectrum, and this turns out to have the structure of a 3 manifold with a boundary. And similar, if you take inside the p-adding numbers, you can take the p-adding integers. It's just a completion of the integers rather than all rational numbers. Then these are the spectrum of the p-adding integers. And it also has boundary, and both ends up having boundary spectrum of the p-adding numbers itself. So this is a 2 manifold. Remember that I claimed earlier that this is like a 2 manifold. So these are like 3 manifolds with boundary, and the boundary is this 2 manifold spectrum of the p-addings. Did you have a question?
Is there a reason why the p-adic completion of integers had higher dimension than the p-adic completion of rationals? Or the spectrum of them?
Very good question. So it's sort of like this. So this is kind of general algebraic geometry rather than something specific to our current discussion. But there's this idea that even in normal algebraic geometry, if you have an algebraic variety somewhere and you take a closed subvariety, there's a notion of taking a completion. I don't know what the best notation is. I think this might be. This is a completion. Maybe it's better to write something like this. This is a completion of z of x at z along z. Okay. along a closed subvariety. So you can just take a plane, for example, and take a line in there and complete the plane along this line. Right? So formally, what it looks like is in terms of the ring of functions. So if the ring of functions of x is here, then this will be defined by some ideal, right? Those guys that vanish on Z, right? And then the ring of functions on Z is OX mod this ideal. So this will be the ring of functions on Z, right? Okay. But what is the completion? This completion here is you take OX modulo higher powers of Z, right? And take the inverse limit of such things. The compatible sequences of functions on X that are might modify, identified modulo higher and higher powers of X, of Z. So this is this completion. So spec of this is what I called a completion of X along Z. So when you do this, what happens is that you somehow still have Z there, right? But you focus very much your attention on an infinitesimal neighborhood of Z. So that's what happens when you perform this operation. So the way algebraic geometers think about this is that this completion becomes like a tubular neighborhood of Z. Except it's kind of an algebraic construction, algebraic analytic algebraic construction of a tubular neighborhood of that. So that's the idea of this completion, right? So this is a very ubiquitous construction in algebraic geometry. Now, what happens is that when you take Z, right, then the ideal P defines a subscheme, right? So in fact, this defines a subscheme. So inside spectrum of Z, we have the subscheme, which I'll call, it's actually spectrum of FP inside here. So this is the zero set of P, right? And if you complete along this subscheme, you get exactly spec of ZP, this p-adic integers. Right? But, so that's the general idea. And but if you take the tubular neighborhood of whatever closed subvariety you have, what dimension should it have? It still has the same dimension as the ambient variety, right? Because it should include these normal directions as well as the direction along the subvariety, right? So this should still have dimension 3. That's a long answer to your question, right? Because you've completed this dimension 3 thing along a closed subscheme. You still have dimension 3. Yeah. Does that make sense? Yeah. So that's a more difficult question, and there we are allowing some poetic license. Okay, so maybe that's okay to explain here as well. So what is, so as I said, so these p-adic numbers are obtained by completing the rational numbers, and p-adic integers are obtained by completing the integers p-adically, right? So this sits inside this, right? Yeah. Well, what is the relation between the two? Actually, this is just ZP with P inverted. This is the way people write this. If you just look at, there's a way of formally starting from a ring and constructing one where any element you want is inverted. Yeah, so that's exactly the same as QP. And you will see this in some of the informal discussions of p-adic numbers. So these things are often represented as power series. When you look at this completion discussion, these things are often represented as power series where these AIs are between, say, 0 and p minus 1, right? And what about the p-adics? That's where the p-adic numbers, the rational completion of the rational, this is where you're allowed to start with some finitely many negative terms. So this is the difference between the two. Yeah? So this is exactly saying that to move from here to here, all you need to do is allow P inverse. Yeah? Okay. Now, but when you do the spectrum, so this is, maybe I should have given a more careful discussion of this. Suppose you take spectrum of A and compare with spectrum of A with some element inverted. right? Then this is an open subset inside here. The effect is to delete the zero set of B when you construct this spectrum. So when you take the spectrum of this guy, this ends up being the spectrum of ZP with a single thing, well, the zero set of P inverted. I'm sorry, deleted. So that's what this spectrum of QP is, just spectrum of ZP with the zero set of P inverted. Now, but the zero set of P so ends up being exactly the same as FP, spec of FP. And this is the thing that was supposed to be dimension 1. Right? And so this is actually ends up being the same as a circle. The arithmetic topology of the spectrum of a finite field has the topology of a circle. So, so what is the point of this? Is that the spec of ZP minus the zero set of P is the same as deleting a circle out of this guy. So then we think about ourselves. So when you follow through the analogy carefully, this thing here becomes something similar to a solid torus. And this is deleting some node in the middle out of the solid torus. So what you end up with is something that's homotopic to the boundary, so the torus along the boundary of the solid torus. So that's the analogy. But so that's the kind of formal analogy regarding these things. But the statement about the dimension itself, there are other more rigorous ways of justifying it once you discuss this cohomology, so the cohomology of these arithmetic schemes. And it has cohomological dimension too. That's another way of stating the situation. That's true, yeah, that's true. But we view that as being homotopic just to the boundary of the solid torus, which is two-dimensional. So for cohomological purposes, it becomes two-dimensional. Thank you. I hope this makes some sense. Anyway. So I would like to, I'm trying to answer that question right now. Yeah, thank you, but I don't know the answer. Very good. Yeah. Well, it seems to be the other way around. As far as we've been able to see so far, you can take standard TQFT and, in a sense, complete it into an arithmetic TQFT. But there seem to be arithmetic TQFT that are genuinely new, that don't come from standard TQFTs. Yeah, that seems to be the direction that the ideas are going. Oh yeah, yeah, sure, yeah. So that was actually, thank you very much. There are many different notions of sewing, but for example, but I was just about to skip that, but thanks to your question, I won't skip it, which is this, right? So for example, therefore, because consistent with this boundary notion, of quantum field theory, arithmetic quantum field theory, you associate an object inside this boundary category or vector space or whatever, right? Because this is the boundary, right? And then in order to get somehow these two pieces, spec Z with one P inverted and spec of ZP cover all of spec Z. So you get this sewing formula that what the quantum field theory associated to spec Z is actually the inner product between these two objects that you get inside the boundary category. So that all works in a nice way. Okay.
Share the same sort of finiteness properties that TQFT.
You mean finiteness like finite dimensionality? Well, I mean, you all know much better than I do. Even that finite dimensionality has to be relaxed often, right? Or even in normal TQFT, depending on what you want to do. Yeah. But so the examples so far are finite dimensional. Did you have a question? Uh-huh.
Well, I just was wondering, why is this called arithmetic? Is it just because of using Z and Q?
Because we are evaluating an arithmetic schemes. The
So does the
the
original matter when it's an arithmetic scheme, or can you define arithmetic schemes over some arbitrary?
oh, okay. So I'll answer that in a few minutes. Okay, go. So as I said, at least this is all very preliminary. Much of this discussion, for example, we don't really have a theory of incorporating higher form symmetries or high codimension defects and things of this sort. Just boundaries so far. But at that level, out of these things, there are lots of interesting examples to my mind of these arithmetic decurved. And at the risk of black boxing some things, I can show you some formulas in a minute. But of course, these shouldn't be arbitrary. I mean, physicists are sometimes probably quite annoyed by the fact that mathematicians treat these things too formally, right? So somehow when it's constructed, it would be great if these things really are constructed via quantization in some way, right? So for example, you should have a picture something like this, right? So for a d-dimensional theory, even if it's arithmetic, if you plug in a d-dimensional arithmetic scheme, you should compute the value by some kind of a path integral, yeah, over a space of fields. That's what I'm putting as that f, right? And the value at some d-1 dimensional space should be the quantization. So I'm choosing the convention that somehow there should be a killer quantization type of thing for d-1 dimensions. And more generally, so there's this general philosophy that the value at d-k manifolds should be a quantization of a k-1 shifted symplectic manifold corresponding to classical fields on this space. So this is a point of view regarding this extended quantum field theory that is pushed a lot by my colleague Pavel Safronov. So what I'm trying to say is that when we're constructing arithmetic quantum field theory as well, they should be quantizations in this sense, not just some arbitrary things. That's what happens in these examples, actually. So that's I'll try to give you a flavor of this. But I don't know how people, I'm not so good at it myself. I don't know how familiar people are with this idea of obtaining the higher codimension values of a topological quantum field theory as a geometric quantization of shifted symplectic manifolds. It doesn't matter that much. Codimension 1, you have a symplectic structure on the space of initial values, right? So, and you can think of the space of associated to the quantum fields as some version of this geometric quantization, right? And we should try to realize that in the arithmetic case as well. That's all I'm trying to say. Maybe not. Maybe that's not the topic to focus on today. So this were, I mean, yeah, sorry. Maybe let's discuss that some other time. Yeah, sorry, maybe I shouldn't have written this. All I meant to say is that the arithmetic quantum field theories as well should also be constructed in some, should really be constructed. You shouldn't just declare that some formal values form a quantum field theory. It would be nice to try to construct them in a manner similar to what happens in physics. I hope this is what happens in physics. Right. So I guess along the way, I've just discussed this. Oh, never mind. So I've just discussed the space of fields, right? So I might want to construct a value for d-dimensional theory on an arithmetic D manifold as a path integral over a space of fields. What could space of fields possibly be, right? In arithmetic geometry. And so as a number theorist, one thing I've learned from physicists is that anything can be regarded as a field. Right? So for you, just take any object. I'm a field, you're a field, everything is a field, right? So I can just take any arithmetic object and regard it as a field, as far as I can see. So more precisely, even with arithmetic schemes, there are various topological features, and in particular, there are various sheaves living on them, right? And fields, in this context, will typically be spaces of sections of sheaves, or sometimes some stacks, right? And arithmetic schemes. And sheaves and stacks, in what sense? Well, there's this notion of a Grothendieck topology. That's a such that you can define on pretty much any scheme, not just complex varieties or not even just arithmetic schemes. And you use these topologies to define notions of sheaves and stacks, right? And regard their sections as being fields. I take the physicist's license and just call them fields in this setting. And then you can try to perform integrals of this sort. So, of course, in order to do that, I also have to discuss how to define action functions for this to be a theory. So this is the challenge, of course.
Is there a way to construct the theory you had on the previous slide using like a Wilson hypothesis as well?
No, not in any obvious sense, because arithmetic schemes do not decompose in the way that normal manifolds do, right? So the usage of the cobordism hypothesis for extended field theories all has to do with the fact that you can cut up manifolds in a very natural way. You don't have that kind of, unfortunately, you don't have that kind of a flexibility with arithmetic schemes. So it's
there have been these like classical gauge sort of and that's a bit different than what we had.
Could you say again? Right.
Kind of looks like
So I think what you are referring to, if I understood correctly, right? Those kind of constructions probably can be used to construct some arithmetic TQFTs. To the extent to which you can take it, I'm not sure. So I think I have two answers to your question, right? If you use the cobordism hypothesis to construct a usual TQFT, I think it will frequently be possible to have arithmetic versions. But I don't think it'll be possible to sort of directly use something like the cobordism hypothesis to directly construct an arithmetic TQFT using the structure of arithmetic schemes, because they don't decompose in the same way. Does that make sense? So like the theory that you referred to, I would strongly suspect that there is an arithmetic version, but it would be by importing the topological version into the setting rather than directly taking apart the arithmetic scheme. Okay, thank you. Yeah, so when you try to push through this point of view, this philosophy, of course, you have to define action function. And that's a fun game. So you take sort of number theoretic objects and what kind of action functions are there that can be useful in studying the objects of interest. By the way, so I wrote up here, so it's like sets of rational or integral points of the sort that you're interested in Diophantine geometry when you're interested in finding rational integral solutions to equations. Right? This can also, from the point of view of arithmetic geometry, maybe I'll be able to get to that in this lecture, these are also mapping spaces. From the point of view of arithmetic geometry, an integral point, integral solution to some equation is also a map from something to another. Yeah? So these kind of spaces of rational integral points can also be viewed as fields inside a nonlinear sigma model, in other words. Yeah? So you can try to use field theoretic ideas in the study of rational integral points as well. Okay.
Like the usual TQFT is like some notion of bell law action. Maybe in a very tensor category, there's some notion of bell law action because the data takes values in some extension, let's say for rationals. What happens here? Like this is So you can have like unusual TQFT, you have maybe a family TQFTs connected by some bell law action.
I haven't thought about that at all, but if your TQFT takes values in some k-linear category, where k is, say, some algebraic number field or something like that, right? I'm pretty sure you can get allo actions on these things as well, although I haven't thought about that at all carefully, but it's plausible that you would get such things, but I don't know. Now, then, in response to your earlier question, what am I doing here in this program? Is I want to learn about defects and the category structures and so forth. By the way, there's always, the number theorists have been studying forever Wilson lines. It turns out, if you look at it carefully, Wilson loops at least. Wilson loops have been studied very extensively in number theory. They turn out to be very important, but we just haven't thought about it that way, right? And so here I'm trying to understand the categorical structure of these higher symmetries and also other defects, analogs of in arithmetic series of the many other kinds of defects, in the hope of turning certain objects the number theorists have been studying for a long time into a more substantial theory, right? So that's what I've been bothering a lot of you with questions and so forth in order to try to come to terms with this. And of course, I would also like to understand these generalized symmetries. So that's kind of a big overview. So what is the point? It's hard to say what the point is. It's kind of fun, right? But in order to phrase this as something sounding more serious, one thing that would be nice to do is to understand zeta functions, L functions, which are very important objects in number theory in terms of physics. If you look at usual constructions of zeta and L functions, number theorists have been looking at this for a while, but they're not very well motivated. Why ever would one be interested in such functions? And it's not so easy to answer the question. Leading number theorists usually kind of laugh at you when you ask this question, but it's because they can't give good answers. Tradition tells you that you should study these things and that they're very useful. But somehow, why such a definition might come about is very hard to explain. And I would like to understand these from a physics point of view. So for example, this is a kind of slightly very complicated formula. And I've tried to put in blue type the very speculative parts of this lecture. The ones that are in black letters are somewhat preliminary, but there are some concrete work related to this. The blue script is all very speculative. So for example, I claimed earlier that spec Z is three-dimensional, right? So if you had a four-dimensional arithmetic field theory, right? And you could regard spec Z as sort of a boundary of this four-dimensional theory, then you'd have some boundary conditions, and the boundary conditions on spec Z for a four-dimensional theory should define something, an object inside, well, this geometric quantization of the space of initial conditions on something like spec Z cross R, although it doesn't quite make sense. So in other words, inside, it should define an object inside the vector space that you're associating to spec Z. The boundary condition should associate a vector inside there, right? And so my own speculation, which is motivated somewhat by work of over function fields of those three mathematicians, is that you should be able to construct zeta functions and L functions in a TQFT way, and thereby giving us better physical intuitions for where such things come from and why they should have some of the properties they have. So this is kind of a very ambitious goal. Construct zeta or L functions as elements inside objects that the TQFT associates to boundaries. So that's one possible goal. I can't do it here. This is purely speculative. Yeah? But in the function phase, yes, they do choose specific boundary conditions for a specific theory. Yeah. And I can't remember what it is, so I won't be able. Yeah, that's right. There's this. There's I should say this. They wrote a paper last year called relative Langlands duality, yeah, where this is all described over function fields for a curve over a finite field rather than spec Z, in other words. Right? But unfortunately, it's a 500-page paper, so it's very hard to pay. If you're ever interested in reading it, I'm very happy to answer whatever I understand about it. In particular, I can point to you specifically where they give a function field analog of this construction. It's not quite an analog of this construction. What they do is they give a construction of the analog of the values of the zeta functions at integers. Right. So here?
Yeah, that equality, you're saying that ZB is, it literally is a category function.
No, because, sorry, let me rephrase. This is a three-dimensional thing, right? And so if you had a four-dimensional arithmetic TQFT, it should associate to spec Z a vector space, right? Yeah? And so this thing will be a vector inside that vector space. No, not a category. Does that make sense?
It's just an object inside the
Inside the vector space. Yes, that's right.
Not the category,
It's just a vector space. That's right. Yeah, that's right. But
it's obvious that you get a
no, of course. But so you can just formally associate. You can say the theory associates the vector space in some way, right? But then you need to interpret the vector space, right? And what I'm claiming is that the vector space can be understood. It should be possible in principle understood as something like holomorphic sections to a line bundle. On a space with a lot of parameters floating around. And one of those parameters should be S. So that's the overall speculation. So you see, S also parameterized. So this is something that's been known in number theory, but maybe isn't emphasized often enough. This S inside this the zeta function actually parameterizes characters of this thing called the Idel class group. So the zeta function is actually not a function, intrinsically it's not a function of a complex number, it's a function of characters. And characters, you see, if you think about characters, of course, they are very much like fields. So if you think about the zeta function as a function of fields, and the right-hand side should be also something like a function of fields, it makes sense. At least the grammar of this equality makes sense. Of such an inclusion makes sense. Does that sort of answer your question?
Yeah.
So sure. So yeah, I'm being very vague about that. Yeah.
It's at least like once category.
Sure, that's right. Okay, so this last thing, I do have some examples illustrating what I mean by this, and maybe we'll have time to get to it. So there was this old idea of people who are interested in the Riemann hypothesis. I'm not that interested in the Riemann hypothesis, by the way. But I'm not so sure why so many people are interested in it. But anyway, people are. And there was this idea that you should try to prove the Riemann hypothesis by relating the zeros of the Riemann hypothesis, of the Riemann zeta function on the critical line, to the spectrum of a self-adjoint operator on some Hilbert space. That was this sometimes called the Hilbert-Polya conjecture or program or speculation or something, right? And if you have appropriate properties of a self-adjoint operator and its spectrum, that should imply the Riemann hypothesis. So such an idea is very old, right? And at that time, it was very ad hoc. Where should such a Hilbert space come from, right? It doesn't make much sense, but I mean, you can try to cook one up in an ad hoc way. So there was some, I'm not by far, very far from being an expert on this whole story. But then at some point, Michael Berry and other people had this idea that you should try to cook up some classical phase space whose quantization should be the Hilbert polar Hilbert space. Right? So that's this. I forgot what it was called, but anyways, they had speculations about classical dynamical system whose quantization should give you should realize this Hilbert and Polya's idea. So my feeling is that if you develop the arithmetic quantum field theory properly, you should get a much better motivated construction of Hilbert space of the sort proposed by Hilbert and Polya. Right? Yeah. So that's another reason one might be interested in this class of ideas. And I'll try to give an example of why one might take such a thing at the end. Okay, good. Yeah, I see that I've already spoken for a while. Sorry, I've already spoken for an hour. So from here, we can go anywhere. Okay, so there was also an example of a Wilson line. Okay, maybe I will give you one more example without too much explanation, with the black boxing a whole bunch of things, just to give you a suggestive, well, some suggestions. I've tried to make some suggestive remarks. Right? So here's an example of a Wilson line associated to a prime. Suppose you take modular forms, right? Modular forms, is everybody okay with the notion of a modular form? These are functions on the upper half plane satisfying some equivariance properties with respect to matrices like this, right? So you take a modular form, and if you take modular forms of this sort, they all have this thing called the Q expansion. You can write it in powers. Well, what is this Q? If you it's a function of z, then Q is e to the 2 pi I z, right? So because of some Fourier series consideration, they all have expansions of this form, right? It's sometimes called the Q expansion. Well, so because it's the expansion of this form f, I'm writing it as A and f, the coefficients here. Right? So here's a kind of amusing fact. If you take any prime, not dividing the level, this is sometimes called the level, the function that takes the modular form to the pth coefficient is actually an example of a Wilson line. Almost literally, if you interpret what number theorists are doing carefully, is actually a Wilson line.
What sense?
Okay. In what sense? So I will explain on the next slide, again with a bunch of black boxes. Right? So here, so there's this famous construction where you go from these modular forms, right, to a representation of some Galois group. So I wrote this as f goes to rho f. So this is the so-called Galois representation associated to a modular form. You get a two-dimensional representation of some very large Galois group. Yeah. So starting from a modular form. And so this is a very long story. And the construction itself is actually quite sophisticated. And it's one direction of the Langlands correspondence. So you can go from modular forms to representations of Galois groups. The other direction is that you can start from representations of Galois groups and end up with modular forms or automorphic forms in general. So it's supposed to be a two-way correspondence in the Langlands correspondence, and this is half of it. Now, but when you have this Galois representation, these kind of Galois groups contain, for each prime, a special element or a special conjugacy class called the Frobenius conjugacy class. This is part of an important ingredient that starts up what's called class field theory. So what you can do, because for each prime you get a special element inside this Galois group, the modular form, you associate the Galois representation, and you can take the trace of the Galois representation along this prime, along this element, right? This arrow is almost the exact analog of a Wilson loop. Right? And then if you compose it with the map from modular forms to Galois representation, you get a Wilson loop on modular forms. But that has a more concrete description in terms of coefficients. Yeah. So this slide is sort of an explanation of what I'm saying. It's Wilson loop. There's a kind of an answer. Okay. More generally, you can consider Galois representations to some group G, right? as being like principal G bundles. Right? Then for every prime, if you associate, to get a more general Wilson loop, you can take a prime and a representation, finite dimensional representation of that group G. Yeah? And that's a genuine Wilson loop, right? And then you can take trace functions associated to that representation. And so what I wanted to say earlier is that these kind of things, number theorists have been studying for 100 years, right? Without calling them Wilson loops. And I guess what I'm claiming is that the Wilson loop perspective seems to be very interesting at the moment. And it gives us a way to reinterpret a lot of what number theorists have done in the past and also do some new things. Yes, yes. So there's inside the topology of these arithmetic schemes, there's a homotopy theory as well. And we can define fundamental group. Yeah. And this this Frobenius element inside this fundamental group, in fact, can be thought of as the class of a small loop that forms part of the fundamental group. And the reason that you only get a conjugacy class rather than an actual element is because the fundamental group requires a choice of a base point, and this loop doesn't have a base point, so you have to choose some path to the base point. So anyway, so I thought this might be at least a kind of an amusing suggestion that there's something interesting going on, right? That you can look at the P's coefficient of a modular form, and that's already an example of a Wilson loop. That would be regarded as a field in this sense. Yeah, that's right. That's right, yeah. So I didn't discuss this here, right? But if you, it's possible to define various action functions of modular forms, right? And you can use that already to construct, say, path integrals over modular forms with inserting Wilson loops, like this. And that's a fun thing to do. I haven't calculated anything, but it's clearly you can define such things. Yeah, so I had a bunch of other examples, which maybe I'll skip here because there's a lot of black boxing going on in this whole story. But maybe what I'll do for with the remaining time, unless there are some other specific questions, is answer some of the background questions that have come up. What are all these arithmetic schemes, right? Simple, right? And how does one have a topology on it and so forth? So in the remaining half hour, maybe I'll explain. Does that seem like a good place to go? I'm very flexible. I've over-prepared many different slides, so I can talk about many things, but this might be one. Is that okay? So, oh, sure, of course, if there are other questions. But maybe if I explain the background, that will generate the appropriate questions as well. So that might be a place to go. So the previous slides essentially lays out the program, that is, what is it I'm trying to do, right? And so probably because I won't get to this, because I probably won't get to this, I will mention that towards the end of this slide, I also wanted to mention this example. You can definitely construct the Riemann zeta function in a very nice way as a path integral of a nonlinear sigma model. It's kind of a very, it looks a bit silly to be giving that interpretation, but it is very interesting. The Riemann zeta function can be constructed that way. And it is suggestive to try to quantize it and construct the Hilbert polar Hilbert space associated to that path integral, which can be, again, can be done over function fields, but not here. Okay, so let me answer some of the questions that have come up about what all these objects are. So first, there was a question, what is the spectrum, right? And so this is the, maybe a good place to start the background. Given any commutative ring with a unit, you can associate to it a space that's called the spectrum of A, right? And do a lot of things with it. So what is this? So the basic definition doesn't quite do it justice, but I'll give you the definition anyways. So there are many definitions. One definition I quite like is this. So you can define the spectrum as the pure states on A. So in other words, so these are just the ring homomorphisms from A to a field. This is the spectrum. So that's yeah, thank you. So I'll say that in a second. But if I just say that these are ring homomorphisms to a field, I hope this seems kind of familiar. So for example, if A were a C-star algebra, this is the so-called Gelfand spectrum of a C-star algebra. Right? But what's the equivalence relation? It has to do with the fact that somehow this field isn't being fixed. That's the main difference when you're discussing spectra of rings like this in generality compared to what you do with C-star algebra. C-star algebra, you have this sort of fixed field C as your starting point, right? But in the spectrum, you can take any field as the target. But that's where this equivalence relation comes in. If you have two states like this, right, and one is obtained from the other by just including this K1 inside into K2, we'll regard them as the same. That's the equivalence relation. Does that make sense? So in other words, just changing the values, we regard them as being the same state. Okay? So that's the spectrum. However, it is interesting to consider this without the equivalence relation, right? Why? Because, for example, if you consider the maps into the homomorphisms to some fixed field K, and the field has automorphisms, similar to Matthew's earlier question, action of a Galois group, right? Then you can act on states with the Galois groups, right? And those are all identified inside the spectrum, but they are also somehow different. So you consider it, sometimes considering the states without the equivalence relation is also very important. Now, if you look at this definition, maybe this is not so important right now, but there are also something called the point spectrum. That's the class of the surjective rho, but the reason for this definition, maybe I won't give right now. We can return to it later if necessary. So there's an obvious way to regard the ring A itself as a ring of functions on the spectrum, right? Because for any element of A, we can just consider the function that evaluates on A, right? Evaluates a state on A. So you get A as a function on the ring on the spectrum of A. So this is one of the ways, anyways, of regarding an arbitrary ring as a ring of functions by kind of this dualizing construction, the double duality. It makes A itself as a ring of functions, except it is very interesting that interesting feature of this, that the ring of function, the values are always moving because this K can be anything. I should also point out that a more common description of the spectrum is as prime ideals. But this other way of describing here, I think it's suggestive because it's closer to physics in some way, right? But also it allows us to generalize, right? Because these are ring homomorphisms. In other words, they are multiplicative, right? And in physics, you consider a lot of states that are not multiplicative, right? Linear maps satisfying some suitable conditions. And depending on the context, it's very common to include this spectrum inside the larger space of non-multiplicative maps that enriches the geometry of this spectrum. This happens a lot in p-adic geometry and leads to some of the work of Peter Schulze, for example. So the starting point of a lot of this is extending the spectrum by allowing non-multiplicative maps. So this viewpoint of view is actually quite important. Now, I'm going to skip a lot of examples and get directly to the definition of arithmetic schemes, because that was the question that arose. So arithmetic geometry is the study of arithmetic schemes. And what are the building blocks? These are spec of A where A is finally generated. Sometimes to stress this, we say absolutely finally generated. So think like this. So in other words, these are, what is the nature of these rings? All you need is 0, 1, and some finite collection of other elements, right? And all other elements are obtained from it by ring operations, right? Addition and multiplication, addition, subtraction, and multiplication. Everything else is obtained from finite collection of elements, right? Using these ring operations. That's what a finitely generated ring is. Right? You get a general arithmetic scheme as a finite union of things like this. That's what an arithmetic scheme is. And in arithmetic geometry, you study arithmetic schemes. And maybe maybe this point is worth emphasizing. You have a completely full-blown geometry over these schemes. You have vector bundles, you have connections, you have fiber bundles, you have topologies, you have cohomologies. Everything works very similar to any other kind of geometry that you're used to. And this is one of the reasons I feel like physicists should be interested in this. So for example, if I would make a comparison, if you compare it to, say, non-commutative geometry, right? This is much more like geometry than a non-commutative geometry. Non-commutative geometry, okay, in some ways you can insist that it's a geometry, but it's a bit artificial in my mind. Yeah, this is very much like a geometry over the complex numbers or anything. You just have to change the formalism a little bit to restrict yourself to rings of this sort. Right? But so these kind of rings, by the way, another way of stating the definition is these are rings that are quotient rings of polynomial rings in finitely many variables over the integers. That's another way of stating what it means to be finitely generated. So the spectra themselves are called affine arithmetic schemes, and then the general arithmetic scheme you get by gluing these things to each other. Finitely many of these things to each other. So and the point, the one reason I think physicists should be interested in this is because these are schemes where the rings of functions have an intrinsic discreteness, of course. Right? This finite generation means that it's intrinsically discrete. And initially, you might think that you might despair of ever doing geometry over such collections, right? Where you only have such discrete collections of numbers to work with. What I'm asserting to you is that over 60 or 70 years, people have developed the geometry over these kind of number systems, right? And it's a full-blown geometry, no different from usual geometry, right? So if you're thinking about the nature of the world, right, maybe it is an arithmetic scheme after all. Who knows if all these continuous systems of numbers actually exist, right? But you can't imagine having a geometric experience without continuous systems of numbers normally, right? But in arithmetic geometry, you can.
The correct type of object uses some sort of not some sort of arithmetic thing, but maybe like not some sort of arithmetic exactly a smooth step. So I would want to see properties of like smoothness of my gate level or something like this. Could you say that like you can relate this to somehow smooth things as well, or there's no relation there?
Oh, well, it depends on what kind of smoothness you want, right? But there's definitely a notion of two things. A notion of a regular arithmetic scheme, which corresponds to being like a manifold, right? And given a map from one scheme to another, x to y, right? There's a notion of that map being smooth, which is really no different from usual manifold notions. And they work in exactly the same way. It depends on what you want to do. Maybe we can discuss this in more detail later. But maybe, in relation to your question, maybe it is worth pointing out. Suppose you take a complex algebraic variety, right? There's always an underlying arithmetic scheme, for which your complex algebraic variety is the set of complex points. There are many such things. They're not isomorphic to each other, but you can always realize a complex algebraic variety as the complex points of an arithmetic scheme. And you can choose different things, and the arithmetic model will give rise to different arithmetic geometry, although they all correspond to the same complex geometry. If you take any compact manifold, you can realize them as the real points of an arithmetic scheme. this is this embedding theorem of Nash and Tonolli, right? That if you're given any compact manifold, just not a complex, just a compact differentiable manifold, you can realize it as a real algebraic set. And once you've done that, you can view them as the real points of an arithmetic scheme, depending on your choice of embedding. So in fact, this seems like very exotic object, but they are underlying structures in a lot of the ordinary geometry that you study. But you can do, the point is, a lot of the geometry you can do directly over this arithmetic scheme rather than passing to the real or complex numbers. I didn't put this on the slide, but maybe I should emphasize something like this. So here's an example of a situation where actually I think there might be some interesting physics, although I haven't really worked it out at all. Suppose you take a complex abelian variety. As you know, this arises everywhere in physics. There might be the Calabi-Yau manifold, and they also get it as from, let's say, conformal field theory, or even in Chern-Simons theory when you try to construct the state space and so forth. Complex abelian varieties are everywhere. In particular, you might have a line bundle on it and a space of global sections. This is an example of a geometric quantization, right, of this abelian variety viewed as a symplectic manifold. So this is a Hilbert space. That this can be thought of as a Hilbert space of some theory. Well, I didn't tell you what the theory is, but this does arise as Hilbert space of some theory frequently. Now, but such an abelian variety often even has a model over Z. So I'll put it. I'll put this as Roman. I'll write there's often an abelian, something close to an abelian scheme over Z, right? Something called an abelian scheme over Z, such that that complex abelian variety is just the complex points of this thing, of this arithmetic scheme over Z. And this line bundle as well, maybe I should put a Roman for that normal line bundle, also has often this arithmetic model. There's often an abelian scheme over Z and the line bundle over that abelian scheme, such that you can get these things there as simply as complex points. So what is the result of all that? Is that that space of global sections, which is a complex vector space, can be viewed as taking the global sections over Z and just tensoring it with complex numbers in this situation. So what I'm saying is that this is a situation where the quantum Hilbert space over the complex numbers can be obtained via a lattice Hilbert space in a natural way, right? So this might be a kind of situation where arithmetic geometry might cast a new perspective on special lattices occurring inside Hilbert space, which of course is very common in physics, right? It's even when you're considering complex Hilbert space, there's special bases that play special roles, right? And so this might be one example where you might see such a thing happen. It's not necessarily easier to compute, but I would say, well, there are lots of things you can do with it. So for example, it has structures that you don't quite see at the complex numbers. So for example, you can reduce this mod P and get FP vector space versions, and you might have a Frobenius section, and there's lots of new structures that emerge via this interpretation. And so so far I've just been speculating about these things, but it should also be possible to do some fairly concrete things with things like this. Okay. So anyway, so I've told you what an arithmetic scheme is now, and said that asserted that it would be good to study these things, right? So in other words, you have discrete, depending on how you look at this geometry here, the observables are naturally discrete, right? So you don't need to go through all rigmarole of worrying about where discreteness comes from. Oh, sorry, yeah. So let's see, what should I do here? Maybe I do have to explain this a little. So in schemes theory, a ring homomorphism from A to B is the same as a map of spaces from spec A to spec B to spec A. So in the formulation I gave, it's sort of obvious. If you had the homomorphism from B to some K, right? By composing with this map, you get a map from A to K, right? So you get this. You set it up correctly. This is an equivalence mapped from ring homomorphisms from A to B and map of schemes from spec B to spec A. So for example, I don't know if I wanted to do this much, but just to tell you some of the number theorists interested in these things. If you just had a two-variable polynomial ring like this, right? Then maps from spec Z to spec A, right? Is just Z squared. It's just pairs of integers. Why? You see, because this is supposed to be the same as a map from this polynomial ring to Z, right? Map from spec Z to spec ZXY is supposed to be the same as a homomorphism from ZXY to Z. But such a homomorphism is just determined by where it sends X and where it sends Y, right? So this is just a pair of integers, like this. So that is a way integer points in various ways get interpreted as map. Now, if you take a quotient ring like this, ZXY mod FXY for some polynomial XY, to consider a ring homomorphism from this quotient ring to Z, well, by composing with this quotient map, it certainly gives you a ring homomorphism from ZXY to Z, right? So in other words, these ring homomorphisms is going to be a subset of the ring homomorphism from ZXY to Z, pairs of integers. But when does such a ring homomorphism factor through this quotient? Remember, this ring homomorphism is determined by assigning a number to X and a number to Y, right? It factors through this quotient exactly if f of those two numbers is 0, right? So when you go through this, in other words, you find that the ring homomorphisms from here to here, right, from this quotient ring to Z correspond exactly to the solutions to this equation. Yeah. That's how, so what am I trying to say is that the integer solutions to equations naturally become interpreted as mapping spaces, right? So this is an old point of view in arithmetic geometry, and people have done a lot with this. Now what I'm claiming is that there's some advantage to be had. It's only beginning. Advantage to be had by viewing these as fields. So I'm now viewing these as fields of a nonlinear sigma model. And trying to define action functions. And so it turns out that some classical functions already long studied by number theorists are profitably viewed as action functions in this context. So maybe the last thing I'll say, since we're approaching the sense. I said a lot of things about topologies, and the general idea is that you can do this very, very generally. And inside very general categories as well, not just these arithmetic schemes. So, but if you're given a scheme, what you do is you designate suitable classes of maps as being open subsets. In normal topology, you have to start with a set and you designate certain subsets as open. And that's what generates a topology. But you can generalize that in a lot of categories by just taking suitable maps as being open. And that's what you can do with arithmetic schemes as well. So then you can have open coverings, right, where you have collection of such maps that give you a surjection. And then whenever you have open coverings, you can also construct these kind of combinatorial complexes of intersections. You have to interpret the intersections a little bit carefully, but in other words, in this case, it's something called a fiber product. More generally, you have to assume some existence of products inside your category. But once you're in this setting, you can see that for every covering, there's a certain combinatorial complex that you get by considering the various intersections. And the idea is that this gives rise to a very rich topological theory of arithmetic schemes and even more general categories. Yeah, this construction by considering the cohomology theory associated to complexes and things like this, and depending on what kind of set maps you regard as open, you get all these things like étale cohomology, flat cohomology, crystalline cohomology, these things, Grothendieck cohomologies that number theorists study. And it's from that point of view that spec Z becomes three-dimensional, right? From the point of view of this kind of topology, curve over a finite field becomes three-dimensional. Curve over an algebraically closed field becomes two-dimensional, and so forth, right? All these previous assertions have to do with some. So from this point of view, although it's not literally correct, I think it's morally correct. It's okay to say that it's very close to the notion of covering dimension. Yeah. In usual dimension theory of normal spaces, there's a notion of a covering dimension, which for the things like manifolds agrees with usual dimensions in a very nice way. And you can think of this as a notion of covering dimensions associated to more general open sets. Okay. Good. Yeah, I think I've already run out of time and probably run out of your patience as well, right? So maybe I'll stop there. And of course, I'm always happy to answer any questions. Thank you.
There were a couple of points where you mentioned reduction module.
Sure, sure.
Do you think about reduction module is some kind of gauging or some kind of
I don't understand what gauging or condensation are, so it's very hard for me to say. But it's an interesting. Now that you mention it, so in arithmetic geometry, you do have diagrams like this, right? So, so actually, I guess I can explain one of the cryptic remarks I made earlier. Sorry, now with slightly more. So if you consider a map from Z to Z mod P, right? There's the opposite direction map from spec of Fp. This is the same as Fp, the finite field element. So spec of Z. And this is supposed to be like the inclusion of a circle inside this three manifold. So this is the analogy between primes and knots, which started up this story long ago. But then, if you have some scheme with a map to spec Z, right? So like this one, right? Because Z is include these functions. If you take, oh, I forgot the specs here. Yeah. But then, because Z is included inside here, you get a map from this spec of this scheme to spec Z. So that's a diagram of this sort. But then you can take the fiber over spec Fp, right? So if this had a certain dimension, right, then the dimension of this thing would reduce by 2. So this actually is codimension 2 inside here. So if you would like to view this as a defect, it would be a codimension 2 defect. And so I mean, so what I said just now, I guess I've been claiming is a useful viewpoint to view things like this as defect. And now whether this can be made to relate to issues like condensation, that's a very interesting question. I hadn't thought about it, but thank you for the suggestion. I will think about that question, see if I understand it, and come back to you with more questions. Yeah. Uh-huh. Sorry. Sure. Oh gosh, yeah. Well, these are They definitely are pure states in the sense of C-star algebra, the same terminology as C-star algebra. Remember, states are pure if they're not a mixture, if they're a convex linear combination of other states. And states of this sort, among all linear functions, I don't think a linear, it's probably, I can't prove it for you right now, but the algebra homomorphism will not be written as linear combinations of two other things. In that sense, it will be pure, but I'm not sure if I'm using the terminology correctly. But in that sense, it will be pure. But I guess for a C-star algebra, there are also other pure states besides the algebra homomorphism. So from that point of view, I think I abused the terminology a little bit. But actually, maybe for commutative C-star algebra, pure states are all algebra homomorphisms. Does anybody know? I think it's actually probably true, but I like to go. Yeah. No, I think, yeah, that's right. Yeah, for commutative C-star, yeah, no, this is actually correct. Yeah, other than the fact that these are not C-star algebras, if you took a C-star algebra, right, you took homomorphisms to C, right? If A is non-commutative, of course, you can have a lot of pure states that are not algebra homomorphisms, right? But if A is commutative, but the pure states should be exactly the same as the algebra homomorphisms. Yeah. It's because if you think about them as a space of operators on a Hilbert space, right? Then when it's commutative, they can be simultaneously diagonalized, right? Yeah. And so the way you get algebra homomorphism is via eigenvectors, common eigenvectors. So they all correspond to actual vectors rather than mixtures. Yeah. Okay, so that's connection. Yeah. Yeah, thank you for the question. I forgot.